All right, guys. So, any questions left over from chapter 2? We made it up through section 2.4 last time. So, anything from chapter 2 homework? I think it was. You had something on. Let me do yours first. Yeah, this is we've got a quick question from the chapter 1 review, the page 127, number 132, right?
Oh my God.
So Margarita is hired
Oh yeah. Margarita.
at a salary of $60,000 a year. 3 years later, it's increased. Can somebody close that door out there? Thanks, man. That's the beauty of.
Can I ask a fast question?
Being
On
next to
the
the parking
exams,
garage.
will we have a little more time than on the quizzes?
On the exam, you'll have 2.5 hours. Yeah.
So
First
the
exam will be a
answer is-
little longer. But
Yeah.
So you'll lecture for an hour and then you have, or 30 minutes or what?
no lecture on the test day. Yeah. I don't give you all the way to
But the
325.
ratio of questions to time is more? Open?
Yeah.
It's like 25.
Also, there will be some questions that are a little more in depth. I mean, the quizzes I try to make nuts and bolts. Quizzes are nuts and bolts. You either know it or you don't. And the test, though, could involve something that's a little more vague or conceptual. Yeah. 3 years later, what was it, 7? Assume that her salary increases linearly. Find an equation that relates her annual salary and the number of years that she's worked for the firm. Okay. So it doesn't look like the problem it is right now because of the way that they gave us the information, but these are points on a graph. When she was hired, how much time has she worked at the place? All right, so
0.
this is T and S of T. So when she's hired, she's been working there for 0 years, and she's making $60,000. So what's this point going to be? 3. Right. A lot of commas, but okay. So now it kind of boils down to, can you find the equation of the line that goes through those 2 points? Right? It sounds very much like a Math 110 question. You just got to find the slope. You've got a beautiful point. Which point there kicks ass?
0.
Yeah, this point kicks ass because it's the B value. It's the y-intercept. So you know B is 60,000. The only thing you don't know is M. Cool. And another way to say that, that's a little more physical, real world, is how much money did she average increase per year? That's the same thing as finding the slope. Your slope would be money per year. Okay. Is that, get you started? Cool. Because all you ask, part A says find an equation. Well, we're almost there. We've got already part of what we need. Now we just got to find the slope. And what's the equation for the slope?
y2 minus y1.
Over.
X2
All right, sweet. Y's on top, right? Rise, run. Rise rhymes with Y, so you can't go wrong. Rise on the top, Y's on the top. Cool. Part B says, where to go? What do the slope and S-intercept of her salary? Slope. So we normally think this is the S-intercept. To be completely honest, this is not what this formula looks like. What's representing an X-type variable? That would be the X-axis. T. What did I just do? And what's representing the Y variable? What's same idea? S. So when they say S-intercept for part B, we understand it to be the same thing as Y-intercept. It's the same idea. So they just want a physical interpretation of slope, which if you were listening, I already told you what it was. And they want a physical interpretation of the S-intercept, which I also told you what it was. I think part C is just actually putting in a value. After 12 years, assuming this continues at the same rate, what will she be making? That's part C. So once you have the equation, part C is simple. Is that cool? Is that? Okay. So what about chapter 2, I think? Anybody have any questions for chapter 2? Yeah.
I do.
What's that? That's all right. Oh, is that, so now you know how to do it? Okay. So be real careful about looking at the problems if it says, if it has a little calculator symbol.
Thank you.
Sure. If it has a little calculator symbol, they're expecting you to do it on the calculator, and very often that means you almost can't do it by hand, so don't drive yourself insane. Look for those little calculator symbols so you know where they want you to do in the calculator. Anything else from chapter 2?
There's the calculator one that was on number 30 on page 160. How would you go about putting those inside the calculator? The points.
Okay, let's look at that real quick here. Well, let's see if I can do this. Page 160, number 30.
Correct.
They ask you to graph that x squared minus x minus 20, so you just put that in y1. And then they tell you what window to use. So you hit the window button, and you want x min to be -2, x max to be 2. Is that cool? So they give you the domain, and they give you the range. So you just make your x's match it, and their y's match it. So on number 30, they say, graph this in your calculator. About the letter. And they say part A says use this window.
Oh, is that what that says?
This means x min, x max, y min, y max. So the calculator normally opens up at -10 to 10, -10 to 10. They say make it now -2 to 2, -5 to 5. So you would find that you just hit the window button, you'll see those mins and maxes. Is that cool?
Yeah.
So it's kind of a nice one to get into it because it's not totally left up to you to figure out what's a good window. They give you options and you can pick which one is. So just so you get used to how to change the window.
And then you want us to draw a picture of what it looks like.
No, all I really need to see is which one works the best. Yeah. So that whole thing about
I see.
the homework is trying to get you ready for the test. So I don't ask you to recreate the graphs, but you should probably be honest how you end up with the answer so you know how to do it. So when the test comes, you won't be freaked out. The tutors in the Math Study Center can certainly help you with the graphing calculator also. And they're supposed to be having graphing calculator workshops. I don't know if I've missed an announcement about those, but I'll try to let you know. They post all the workshops in the Math Study Center, and they do have like basic graphing calculator workshops, and then they have some more advanced graphing calculator workshops later in the semester, so you might want to look out for those if you're relatively new to it. The basic one assumes you're not sure where the on button is, so that's just to let you know where it starts. And then they get to the end of the thing, they're doing a few basic graphs. So, any other questions from? Yeah. Oh yeah. The first day I gave out the homework sheet, and it's up on the website too. It's called the Timeline Homework Sheet. Something else in there. Yeah. Number one, you would not want a multiple choice test made by me. Because it would be one of those multiple choice tests that maybe some of you have heard of, that you can make multiple choice tests difficult. And to me, it's just adding extra crap on top. And it's just a lazy teacher doesn't want to grade. Just stuff them into a machine and grade. So normally I say if you have a math teacher that asks you to bring a Scantron, they're not a real math teacher. Right? Math is all about, at this level, when you're learning math, it's all about the process. That's why if you get the wrong answer, very often I'll give you most of the points just because you made some little mistake somewhere else. So it's all about the concept. You get the concept down. When you go out and get a job, and your boss says, how much money are we going to make next year? And it's supposed to be negative 60,000, and you tell them 100,000. Well, you're probably going to get fired. That means a lot. Here, though, it's if you did all the work right and you made one little mistake, you're going to get most of the points because they grade heavy on concept. Cool. So I don't understand math people that use Scantron tests. That's just lazy BS. But because it's all about the process, and I don't see how you see any process if you let a machine look at little dots. I think my position on that is clear. So I don't want to see any Scantron in this. If you got one for later class, keep it hidden. I don't want to see those things. That is for other classes. Any other questions? Okay. We made it through 2.4 last time. And we actually did a little tiny bit out of 2.5. And what we did last time was just to look at some very basic idea. We started with a square root function. And that, of course, has this shape here. And if I come in and I say, okay, what about what two shifts, two transformations, what two shifts does that thing represent? Okay, that's going to be right, one. So it's with the x, so it's going to be left or right. And that's outside, that could be put with the y, so that's going to be up or down.
Down.
So that's definitely down, 2. Cool. And I know when you first look at it, it's a little counterintuitive because you see a minus sign and you're like, why are we going in the positive direction when there's a minus sign? But I'm hoping that it made sense. Your inputs have to overcome that minus one, so there'd be one bigger. That's the whole idea behind that. So now you take every point and you go right 1, down 2, right 1, down 2, right 1, down 2. And now G is there. Cool. Not too bad. Yes? Okay. So what about this kind of thing? What if I had what more color? Yeah.
Negative, it flips it upside down?
I like it. So think about it. It's affecting the outputs, right? The function used to be square root of x, so all the outputs were positive. Now the function is now negative of what it used to be, so all the outputs are the opposite of what they used to be, additive inverse of what they used to be. So 0 won't go anywhere. 1 becomes negative 1. You guys with me so far? And then 2 becomes negative 2, so now it's there. So it kind of completes that parabola. That's the missing bottom section of the parabola that fell over. You guys, is that cool? Okay. That's kind of nifty. Maybe? Yes, ma'am. Yes, cool. Look at you with your ESP. What do you think I have to do? Why does it not exist over here?
That's negative numbers and square root.
Yeah, and whenever we talk about graphing these things, we're not graphing on the complex plane yet. We won't be at all this semester, by the way. But we need real outputs. So I can't have any negative inputs when I have a square root of x. But look at, what can I do then that would allow negative inputs? If the first thing I do to it is change the sign, like that. Now part of your brain balks when you see that, because part of your brain goes, there's a negative under the root. But that, all that means is all the x's then have to be negative themselves.
So it takes it to the other side.
So if it's out here, it's going to be a flip around the
Axis.
X-axis, right? So this is a flip around X-axis. If it's out there, it's flip around the X-axis. If it's in here, flip around the Y-axis. And if you think about it, I really want to make sure that this becomes a cohesive thing. If I said if it's in with the X, it should affect the X kind of, and it does. If it flips around the Y-axis, then that does affect what X's are being used. You kind of with me? And again, I don't necessarily like to memorize everything. It's just a real quick second to say to yourself, okay, that's going to change the domain pieces. That's going to change the outputs. I don't even think about flip around which axis because it's real easy to mix those up if you try to memorize it. All right. How does it far? Okay. So now for this guy, it's going to take everything. So 0 stays 0. That used to happen at 1. Now it's going to happen at -1. That used to happen at 4. Now it's going to happen at -4. Okay. All right. So there's that spaghetti happening already. So I don't think I'll do any more on top of that. So how do you feel so far about those? You've got just picking it up and moving it around, left and right, up and down. Now you've got just mirror imaging it around one axis or the other axis. Right? So what the hell else could we do with these things? I like it. Stretch it, compress it, in either along the x-axis or along the y-axis. You can stretch it or compress it. And you've already seen this kind of thing. What happens? You guys got this here? I don't know if you guys remember this, but there was something about the coefficients of parabolas, for example. So here's your regular old standard parabola. Okay. But if I decide instead of that to have like this, does it get fat or does it get skinny? Yeah, because that is sort of still, it's still actually, when you get to calculus, you'll learn that this is pretty much exactly what's going on. That's still part of the slope. So it's really increasing the slope. I'm making it was 1, now it's 2 in a way. It's not the slope, but it's related to the slope. So it's going to go up faster, which is going to make it skinnier. So now, whatever the output was at 1 is now going to be twice what it was. So at 1 it went to 1, now it goes to 2. At 2 it went to 4, now it's going to go to 8. So this thing is going to be nice and skinny. Whoa. How are we feeling there? And again, it's a little counterintuitive because it's a number bigger than 1, but it makes it skinny because it is sort of related to the slope. It goes up faster. Or down if it was a down parabola. And finally, so what if I put in there I don't know, 1/4?
Wider.
Yeah, so this one's like a stretch. It stretches it. It takes it and just pulls it up. This is somebody sat on it. Compression, right? So this would make every output is now 1/4 what it used to be. This is now at 1/4. This is 4, so now it's at 1. I guess, is that cool? Whatever it used to do, it's now 1/4 of that output. So a normal parabola at that point, untransformed parabola would be at 4 for an input of 2. Now it's 1/4 of 4. Now it just goes to 1. It's been smushed. It's the technical term. Cool. So if you do want to commit these to memory, I'm not going to stop you. It's just that it doesn't require that. The people that do better in math are the ones that realize that they don't have to memorize every damn thing. They just allow for the fact, I just got to think for like 2 seconds about the situation, and then I can do it. I don't have to memorize it. It's not going to save me enough time to waste brain cells. Right? You want to learn an idea and then apply it instead of memorize each piece. That's why people that do poorly in math, they feel like, how can I never do this? How in the world do you remember all this shit? Like, I don't. I remember a few key things that tie everything together. I just take a couple seconds in each situation to think about how it applies there. Okay. Oh, so here we go now. So this is along the y-axis what it's going to do. Is it going to stretch it up or push it down? Cool. Of course, if it was opening that, so it's like pushing it like this or stretching it like that. So if I had a graph, if some of the problems you'll see in the book don't even tell you what the function is. They'll say, here's a function f of x. It's this. And they say, okay, now graph a rough sketch of what this would look like. So what's going to happen?
I'll erase it.
Yeah, this is going to be taller. This is going to be lower, right? It's going to be 3 times whatever the output used to be here. It's going to be 3 times that now. So it's going to be up there for that. It's going to be wherever the hell that is. It's going to be down there for that. Cool. Is that cool? So that's just more of just a general idea. It's not as specific, but to me it's almost more important. Just the concept of what's going on. So the one thing we haven't done yet is, what about pushing it or pulling it this way along the x-axis? Which actually, now let's see who's got the concept down. In order to affect along the x-axis direction, the stuff that I'm doing has to be actually in with the x. That's the idea. So if I have, let's see. Let's go back to the square root for a second. So I got my square root. And I want to like a spill card. I don't like it. It's just way too ambitious. I want to push that thing back in. So I want to compress that thing in. See if you guys, if I wanted to move it to the left, what would I put inside? Let's say I want to move it to the left 2. I put +2. I got to kind of do the opposite thing, right? So if I want to compress it, make all the inputs smaller, let's say by a factor of 3. What do I put in here? Do I put a 1/3 or do I put a 3?
3.
Exactly. It's kind of the opposite of what it looks like, right? If I see a 3, I'm thinking it's getting bigger. It's actually getting smaller because all the inputs have to react to that. So if I have this, to get the same effect, to get the same output, my inputs now have to be 1/3 as big. Because the first thing I do to it is triple it. So now, it used to take up to 4 to get an output of 2. But what gives me a 4 in here? What x value would give me a 4 inside? What would make this 4? 4/3. Wouldn't that then be a 4 inside? So it used to take up to 4 to have an output of 2. Now that I put that 3 in there, it only has to go up to 4/3 to have an output of 2. So now at 4/3, about right here, it's going to have an output of 2. It used to have to take up to 1 to get an output of 1. Now it's only going to take up to 1/3 to have an output of 1. So now that's been smushed in. I'll let you guys absorb that a little bit. So obviously if I wanted to stretch it out by a factor of 3, that's when I would put in a 1/3. Okay, maybe. All right, so when I have something like this, it actually does the opposite of what that looks like it's going to do at first glance. It actually makes it go back 7. This makes it look like it's going to get bigger, but it actually pushes it back and makes the x values smaller, and that's just because they are allowed to be smaller now. The first thing that thing does to it is make them bigger already, so it can be much smaller than it used to be to have the same output. All right. Now, I want you to realize, you certainly could make a table of values for this thing and graph it, so the worth of transformations might not be immediately apparent if you've thought that far. Why in the world are we doing all this shit when I could just plug the numbers in and graph the damn thing directly? I don't blame you for thinking like that, but the honest answer is transformations become huge later, especially when you start learning more complicated transformations. You want to learn shortcuts for those. So you have an ellipse and you actually want to rotate a little bit. That's one we're not going to talk about this semester. It's a little more difficult. But you want to know how to do that. It's the same kind of idea. You want a general rule for what makes that happen and how to control the angle that it actually gets rotated by. I think, yes. One last thing. I'm going to give you guys a few problems to try on your own. One last thing is the idea of symmetry. And there's a lot more symmetries than what we're going to talk about right now. We're going to talk about two very basic ideas of symmetry and how to tell when they are happening on a graph or from a function. You have even symmetry and you have odd symmetry. And there's a few places in calculus where knowing ahead of time if your function is even or odd is going to make the calculus to do with it easier. Sometimes even 1 second worth of time instead of all day, if you just pay attention to the symmetry. So an even symmetry would be something like that, it's symmetric with the y-axis. And why do you think we call it even? Because this has x squared, or x to the fourth, or whatever, some even power. So even symmetry is another way of saying symmetric with the y-axis. The y-axis is the location of the mirror. Okay, cool. So, it doesn't mean that only things with even powers are evenly symmetric, because I can think of a very quick one which does not have an even power, but it's still, it's absolute value, right? So incredibly enough, odd symmetry must be something like either cube root, or even more basically, straight line. Now that one, because they have odd powers, so they're sort of related to those. It's a quick way to remember the definition, is to think about even and odd powers. But what the hell is going on there? This is easy. This is just symmetric to the y-axis. That's easy enough because it's the same thing there as it is there. What is that all about? What kind of symmetry is that? It's not symmetry. It's not x-axis symmetry, right?
Quadrant symmetry.
Okay, I like it. It's a good attempt. Like quadrant symmetry almost. Cross-quadrant symmetry. I like that. CQS.
Is that not a thing?
It could be.
It is now.
It is now. But it's actually called symmetry through the origin.
Oh.
Because if I take like 2, pretend like that's 8. Screw. Over here, -2 would go to, if it's a cube, what's -2 cubed?
-8.
-8, right? No, it's negative. So it's called symmetric through the origin because if you draw a line through it, actually, if you take that and draw a line through the origin, equidistant on the other side should be where the other point is. That's why it's called origin symmetry. Symmetric through the origin is another name for odd symmetry. Okay. Exciting. So how do you tell if you don't have a graph? Here's a little more concise definitions, a little more rigorous definitions. Actually, I put a test for. So when you first see this, it's kind of like, okay, what the hell does that mean? And then once you understand what it means, it's like, well, how the hell do I use that to do a problem? Let's look at first what it means. Even symmetry says if 2 squared is 4, negative 2 squared must be 4. That keeps that symmetry across the y-axis. Is that cool? And that's exactly what this says. If you put in negative, f of 2 must be the same thing as f of negative 2 in order for it to be even. Actually, it says it the other way around. It says if that's true, then it is even. Symmetry. And this one says, all right, well, 2 cubed is 8. Let's go to the right picture here. 2 cubed is 8. Negative 2 cubed is negative 8. That's exactly what this says. If you plug in the opposite value, you should get the opposite output. Okay. How's that going so far? So if I give you a problem like test f of x equal to or symmetry. So I think most of you kind of understand what this is saying. So now the next level is, how the hell do I apply it in an actual problem? Well, I know what f of x is. I just have to compare that to f of negative x. And that's should not be a big deal. We know how to handle throwing in anything into the function. So f of x is this. What's f of negative x? And negative x cubed minus 3 over negative x to the 5th power. How are we doing? We know that's what functions mean. Just replace the x with what's in there now. Well, what's in there now is negative x. Now what's negative x cubed? Negative x cubed. Negative x to the 5th. Now obviously it's not even because it didn't come out to be the same as what it used to be. You with me? When I plug the negative x in, did I get the same function back? Hell no. Did I get the opposite of the function back? The correct answer again is
No.
hell no. What's the opposite of this? It would be negative x cubed plus 3. You with me? That's not what that is. In fact, all those negatives cancel, right? So you actually get x cubed plus 3 over x to the 5th. That's not what it should be in order for it to be this. So does it have either of those symmetries? Good. I like it. No. Yes, sir.
How about x to the fifth? Should we change the sign of the opposites?
Yeah, it did change the sign, right? Because the fifth, raising a negative to the 5th, it's still a negative. Cool.
So it's a neither symmetry? Or it's a neither symmetry?
I like it. It doesn't have to be either of these. In fact, I could very easily, this has even symmetry, this has no symmetry. Or at least not symmetric according to even and odd. Thankfully later, this still is symmetric. It's just not symmetric to the origin or to the y-axis. So it's not officially even or odd. How you guys doing? So it should almost be strange when you have a function that is actually even or odd. There's a smaller set of those than all the functions that you could possibly imagine. Yeah?
How did that become positive? The function plus 3?
All the negatives cancel. Right?
You only negative the x's.
All the negatives cancel. Is that cool? Take a negative out of the top. It cancels with the negative on the bottom, so everything's positive at the end. Is that cool? Good. Be real careful. I can't just cancel these two and go, no. This is also being divided by a negative. It also must change.
Are you multiplying by negative 1? I don't understand.
So if I have, is everybody cool with what I've got here? Everybody's cool with getting there, right? Yeah. So now, take a negative out of the top. What do you get?
X equals x 3.
Okay, now those cancel.
Oh.
Okay, so then you get x cubed plus 3. It's actually the same thing as if I have 2x plus 6 over 2. And then the mistake I always get in algebra is that. What mistake did they make? They forgot to apply that to this also, right? So that should be a 3 there. Well, that negative kills that and that. They're both being divided by it, so that negative kills them both. One fell swoop. Grace is not using that. Is that cool?
So do we always have to remember those two equations? You know, we don't have to determine like which symmetry.
Yeah, all you got to remember is plug a negative x in. If it's the same, it's even. If it's exactly the opposite, it's odd. If it's neither of those, it's neither. Yeah. So all you really have to remember is this step right there, and then, you know, if you plug a negative x in, if it stays the same, it's even. If it changes the sign completely, it's odd. So here's one. Let me show you one that's actually truly one or the other. And then I want to see if you guys can realize what it was that threw that guy off. This looks like it looks like it wants to be odd. You with me? Because aren't all the powers I see odd? There is one other power that you don't see that throws that idea off a little bit, though. So we'll see what happens. Here, what's the first step to test this? Throw a negative x in. Right? That gets you started. That's all you got to remember. As a test for symmetry, you throw a negative x in. And then hopefully your brain remembers what the hell to do next. But first step is throw a negative x in. So then I get negative x to the fourth, twice negative x squared. And of course what happens with each of those negative x's I just threw in there? Yeah, they all become positive because they're all to an even power. So that is the same as that. Cool. So the little trick, the little interesting thing is, what is actually on this 5? There is an x to a power. Does somebody know what that is? I like it. There are 0 x's, so there's an x to the 0. And essentially, 0 is really officially neither even or odd, but if it had to be one or the other, it would be even, because it's 2 away from 2. All odd numbers are 2 apart. All even numbers are 2 apart. You kind of with me? So look at this dude. That was the odd. Good job, Jeff. That was odd. That was odd. But this guy is essentially even. So that's why it ended up neither, because it's a mix. How could it be one or the other when it's got both of them in there? You guys kind of with me? So if I would have done this, number one, he could have simplified it. But number two, now they're all truly odd powers. Then it would actually be an odd function. Yeah. Where did what's that?
No, it's a mixed function. And that's neither.
Oh, that's 3. Sorry. Just as I move along, my 3's become...
They're a mixed function.
Sorry.
Doodle.
How you guys feel about that idea of symmetry? Yeah.
So all we're doing is pretty much taking x, negative x.
Yeah, and then stepping back. And then you make x negative x. You simplify what you just did. And say, is that the same as it used to be? If so, it's even. That's the same as it used to be, it's even. If it's the exact opposite of what it used to be, that's odd. If it's neither, it's neither. So there's not that much to memorize. Do you understand what I'm saying? So don't look at this and say, memorize this, memorize it. No. Do that no matter what. And then it stays the same as even, but that's how you kind of organize it in your head.
We did a problem like this, and we got a test. Are we always going to get a given before it? Like given F?
Yeah. I could do it graphically. I could give you a graph and say, does this look like it's even or odd? And that's obviously going to be odd. But yeah, otherwise they got to give you the function to test. If they don't give you the function or a picture of it, there's nothing for you to work with. Yeah.
So 0, 2.
Say again? Yeah.
Can you explain when you said it was given?
Yeah, this guy is neither. Yeah. It's not even because it didn't come out to be the same as it used to be, and it's not odd because it didn't come out to be the opposite of what it used to be.
So it must be on one side or the other.
so it's just neither. Does that make sense? So, I mean, I don't have a clue what the hell it could look like, to tell you honestly, because all it has to do is not be symmetric to the y-axis and not to be symmetric to the origin. So, I mean, for all I know, it could look like that. Probably not. You guys kind of, is it cool? Yeah.
Is it gonna be like a truth that every time you have like all even exponents and all exponents, it's gonna be the other?
Well, for the most part, it just depends on how they attach them together. Does that make sense? I mean, if you just make like polynomials and ratios of polynomials, that's nice. That's no problem. If you start throwing in some other functions in there, it might throw it off. Especially functions that mess, like if you have a radical in there, you're not sure how it's going to affect that piece of it. Does that make sense? Cool.
So for the example, for it to be odd, it would have to be x cubed minus 3 x over 5. I mean, x to the third.
In order for this to be odd, and that's a good question, let me do it like that. So this started off like this. In order for this to be odd, you write this down. F of x f of negative x must be what?
Negative.
3 plus 5.
To be odd. Now, is anybody wondering why it's not that?
That's a good cancel.
If I put a negative on the top and a negative on the bottom, they cancel. It's not really different then. To be truly different, you just multiply the top. So, or you could do this. Those are the same. Mind blown. All right. But really, those kind of things dealing with fractions, we need to kind of be over it. If I want to change the sign of a fraction, I can't change the sign of the top and the bottom because I've effectively just done nothing. Because everything I just did cancels. What good was that? Is that? You say about face and the dude spins all the way around. Like, what the hell is it? Yeah.
So if we have a negative at the very first, like right here, we have negative x power 3 plus 6. Instead of 5, we have 6. Does it still consider as an odd symmetry or not?
It doesn't matter what that number is.
No.
What matters is the fact that it's a constant. Because a constant automatically means a 0 degree term, right? X to the 0, which is effectively even. Is that cool? No. Even numbers go, let me start counting down. 8, 6, 4, 2. So then 0, if it's going to be anything, would be considered even. And for these tests, it actually kind of, you can treat it as being an even part. If you want to just kind of look at it and kind of tell ahead of time without doing work. The more you understand, the less you got to do. So if you saw a problem like that and you wrote, well, those are odd, but that one's effectively even, so it's neither, and you didn't do any of this work, tear. I mean, that's exactly what you want to have happen in math. Understand it well enough that you don't have to do all the little busy grunt work, really. Okay. Not that this is not important. But it just gets the idea in your head, so you effectively get to the point where you just look at a function and tell, is that even or odd? So when we get into trigonometry, which will be brand new functions for most of us, possibly. I don't know if you guys have already seen a little trig in high school, maybe. Then we can start bringing back this idea of even and odd, and in fact, it will come back. And it will definitely come back in calculus, even and odd. Okay. You guys want to take a break? All right. Come back at 1/4 past. This guy's still going?